All right, this is a continuation of our notes from Target 3.2b, 4.3 DFG. Remember, we're still in Chapter 16 talking about covalent bonding. Now remember, covalent bonding is the sharing of electrons. We talked about polar covalent bonds and nonpolar covalent bonds, where in polar covalent bonds they're sharing unequally. Nonpolar covalent bonds, they share equally. In order to determine whether or not they share equally, you look at the electronegativity differences, which is just telling you which one has a stronger attraction for the shared pair. We also talked about the types of bonds you could have when they're sharing. You can have single, you can have double, you can have triple. Keep in mind when we're talking about like a single bond versus a double bond, and then again compared to a triple bond, you've got one shared pair. One from each atom. Here you have two shared pairs, 2 electrons from each atom. Here you have 3 shared pairs, 3 electrons from each atom. Keep in mind that these have the strongest attractive forces between them, where this would be considered the weakest. Okay. So in other words, these have a higher bond energy, or these would have a lower bond energy. Now, we have compared ionic compounds before with covalent compounds. We know that ionic compounds have very high melting points, where molecular have low melting points. That's due to their attractive forces. Again, with ionic, you've got your positive and negative ions that have very, very strong attractions for one another. One positive ion gets completely surrounded by a negative ion. Those negative ions get surrounded by positive ions. And so you have a strong attractive force all around. When we start talking about molecules, we have to talk about what we call intermolecular attractions. Now, your intermolecular attractions are those attractions that are between the molecules. So you would have a water molecule. Okay, these are bonds. But when another water molecule comes over, and they attract to form a water droplet, you get different attractions in here. Okay, and you have an attraction there. That is your intermolecular attraction. Oops, I can't. Intermolecular attraction. Sorry about that. Okay, so they attract to one another, and that's what sticks them together. And so kind of like butter. When you have a stick of butter, you have a lot of molecules that are attracted to one another. Now, in the refrigerator, it stays nice and solid, but you bring it out, and it gets very soft. In the summertime, it could even melt if you just leave it sitting out in a room. That's because these attractions in between the molecules are very weak. So what we want to do is look at what kind of attractive forces exist between molecules. The weakest forces collectively are called van der Waals forces. There are actually 2 of them, so keep in mind these are the weakest. Okay. The first one is called dispersion. This is the weakest of all. Okay. It is the weakest. This is caused by the motion of electrons. Okay. We see this a lot in our halogens. So a good example, halogens. We'll compare chlorine, bromine, and iodine. Remember, they're in the same family because they have a similar electron configuration. So they have some similar properties. But chlorine is a gas, bromine is a liquid, and iodine is a solid. So right there, just having different phases, we know that they have different attractive forces. So this would be the weakest of the 3. This would be the strongest. Now when you look at these, you've got chlorine and chlorine. If you look at electronegativities, 3.5 and 3.5, that's 0. So this is non-polar. So it can't attract to itself because of opposite poles. So same thing with bromine, same thing with iodine. So what makes them attract? So if you take a closer look at how these come together, they do share equally. So let's say that's a nucleus and that's a nucleus. Because they share equally, they kind of have this cloud around them. Okay? But electrons are moving in the outer level. And so when you get two of these close together, as they are moving, there's a possibility that at some point you might have more electrons on this end. And if it's close to this one, that's going to cause the electrons in this one to come to this end, kind of repel. And so this is what we call like a slight dipole. Okay. You get, for a little bit, you get a slightly negative here and a slightly positive here, slightly negative, slightly positive, due to the motion of the electrons moving around. And that's what's going to bring them together. Now, why does that not work for chlorine? Well, because chlorine has less electrons, where iodine has more electrons. These are in order in the periodic table. You've got chlorine, then bromine, then iodine. So you have more levels of electrons as you go down. So the more electrons you have, the more likely it is that this situation can occur. And because iodine is a solid, we do know that that is occurring in that example. Okay, the second van der Waals force is actually the dipole interaction. Okay, so this is going to occur between polar molecules. So occurs when polar molecules attract. Okay, so remember, in order for them to be a polar molecule, they would have to have polar bonds as well as the correct shape. They would have to show that they have a slightly positive and a slightly negative end. Again, that's like ammonia and water. Again, we saw with water, hydrogen is the slightly negative one, or a slightly positive one. Oxygen is the slightly negative one. Even when we talk about ammonia, we usually see solutions of ammonia in the store. They're aqueous solutions mixed with water. Remember, ammonia has that trigonal pyramidal form. Slightly negative, slightly positive, slightly positive, slightly positive. These would arrange so that this end would actually attract to this end. Okay? Because they have the slightly positive, slightly negative ends, they can attract to each other. That's why you always hear that term like dissolves like. So water can dissolve ammonia. However, water cannot dissolve things like oil because oil is nonpolar. When we talk about the dipole interaction, it is very similar to the electrostatic attraction that you see in ionic compounds. However, it is much weaker. Okay, so this is not a strong attractive force. And then depending on what kind of molecule you have, it can vary. Like ammonia, if you open up a bottle of ammonia, you can smell ammonia because it does have a weak attractive force. Therefore, it will turn into a gas fairly easily. So now we've covered both van der Waals forces. Again, dispersion, which is caused by the movement of electrons, and dipole interaction, which occurs when polar molecules attract to one another. Again, those are the two weakest intermolecular attractions. The strongest of the intermolecular attractions is called hydrogen bonding. Hydrogen bonding. Okay. This is not a van der Waals force, but it is an intermolecular attraction. Now, in order to have hydrogen bonding, you need two things. First, you need to have hydrogen. You can't have hydrogen bonding unless the molecule has hydrogen. The second, hydrogen must be bonded to an atom that has a very high electronegativity. Remember, electronegativity measures the atom's ability to attract electrons in a shared pair. Okay. Most typically, hydrogen bonding is going to occur when hydrogen is either bonded to oxygen, nitrogen, or fluorine. Okay, oxygen, nitrogen, or fluorine. Those are three of our higher electronegativity atoms that hydrogen will bond with and produce hydrogen bonding. Now, why is that the case? So let's go back to water. Obviously, water could have hydrogen bonding. Now remember, we already know that water is slightly polar. Why is water slightly polar? Again, because oxygen pulls the electrons away from the hydrogen. Now what's happening is it makes the hydrogen feel like it doesn't have any electrons because they're pulling so hard on them. And then when we look at oxygen, nitrogen, and fluorine, they also have another special feature. They have some lone pair of electrons. Okay? So when another water molecule comes in, you've got oxygen with its lone pair of electrons, and you've got your hydrogens, and this hydrogen feels like it doesn't have any electrons because this oxygen is taking them. When another molecule comes close to it that has a lone pair of electrons, hydrogen says, hey, I can have those electrons. And that will give us a hydrogen bond. Okay, so it seeks out that lone pair of electrons. So oxygen might pull this one, this pair right here, closer to it. So hydrogen is going to say, hey, I'm going to take these. I'm going to attract those. So it's not a true bond. That's why it's called an intermolecular attraction. But it's kind of similar because it does attract those two together. Okay, so now we're just going to summarize it really quick. We have 3 intermolecular attractions that we can see between covalently bonded molecules. Okay, so when we have actual molecules, you have dispersion, you have dipole interaction, and you have hydrogen bonding. Remember, these two are known as the van der Waals forces. And as we go down, they get stronger. Okay. You should be able to determine whether or not a molecule has dispersion, dipole interaction, hydrogen bonding. Remember, dispersion is typically for non-polar molecules, and it's caused by the movement of electron within that molecule. Your dipole interaction is when you have a polar molecule, so you have to have a polar bond and a bent shape or a trigonal plane or a trigonal pyramidal shape, something that allows you to separate the charges. And then with hydrogen bonding, you have to have an atom that has hydrogen and is bonded to oxygen, nitrogen, or fluorine.